So here's something to think about as you settle in tonight. Imagine you've got a coffee mug sitting on your desk. Just a regular mug, handle on the side. Maybe there's still a little bit of cold coffee in the bottom. Now imagine you've got a donut sitting next to it. A plain glazed donut. Nothing fancy. And I want to tell you that to a certain kind of mathematician, those two objects are the same thing. Not similar, not kind of alike, the same. And that statement, which sounds completely absurd on the surface, is actually one of the most profound and useful ideas in all of mathematics. It's the kind of idea that helps engineers design robots, helps physicists understand the shape of the universe, helps biologists decode the tangled structure of DNA, and helps your phone figure out the fastest route through traffic. And the story of how we got there, how human beings slowly, painstakingly figured out that shape itself could be a branch of mathematics, that you could study the properties of objects that don't change even when you stretch and bend and twist them. That story is one of the most beautiful in all of science. It stretches back centuries. It involves some of the greatest minds who ever lived, and more than a few people you've probably never heard of. And it starts, like a lot of great stories in mathematics, with a puzzle about a city and its bridges. But before we get to those bridges, let's just sit with this idea for a moment. Because topology, which is the name for this whole field, is genuinely unlike any other kind of math most people encounter. When you think about geometry, you think about measurements, angles, lengths, areas, the precise distance between 2 points. Geometry cares about exactness. It cares about whether an angle is 90 degrees or 91 degrees. Topology doesn't care about any of that. Topology is what you get when you throw away your ruler, throw away your protractor, and ask a much stranger question. What properties of a shape survive when you're allowed to deform it? Not cut it, not glue new pieces onto it, but just smoothly stretch it, compress it, bend it, twist it, like it's made of perfectly flexible clay. What's left when you strip away all the rigid measurements? And it turns out quite a lot is left. In fact, some of the most fundamental properties of a shape are exactly the ones that survive this kind of deformation. The number of holes in it, for instance, whether it has an inside and an outside, whether you can get from any point on it to any other point without leaving the surface. These are topological properties, and they're surprisingly powerful. That coffee mug and that donut, they both have exactly one hole. For the mug, it's the handle. For the donut, well, it's the donut hole. And if you imagine the mug is made of soft clay, you could, in principle, smoothly reshape it into a donut without ever tearing the clay or poking a new hole in it. You just gradually shrink the cup part, fatten up the handle, round everything out, and eventually you'd have a donut shape. A torus, mathematicians call it. No cutting, no gluing, just smooth deformation. So topologically, they're identical. They have the same fundamental shape, even though geometrically they look nothing alike. And that distinction between what geometry sees and what topology sees is really the heart of the whole subject. Now, the person who arguably started all of this, or at least planted the seed that would eventually grow into this enormous field, was Leonhard Euler. And if you know anything about the history of mathematics, you've probably run into Euler before, because the man was everywhere. He was born in Basel, Switzerland, in 1707, and he is, by almost any measure, the most prolific mathematician in history. He published more than 800 papers and books in his lifetime, and he kept producing work even after he went blind in his later years. He'd dictate papers to his assistants, holding the entire argument in his head, equations and all. The sheer volume of his output is almost incomprehensible. When he died in 1783, there was such a backlog of unpublished work that the St. Petersburg Academy kept publishing his papers for nearly 50 more years after his death. The man had been dead for half a century, and new Euler papers were still coming out. It's one of those facts that makes you just shake your head. But the particular thing Euler did that matters for our story happened in 1736, and it involved the city of Königsberg. Königsberg was a Prussian city. It's now called Kaliningrad, and it's part of Russia. And it was built on both banks of the Pregel River, which had 2 large islands in the middle of it. The city was connected by 7 bridges. 2 bridges connected the northern bank to one island, 2 connected the southern bank to that same island, 1 bridge connected the 2 islands to each other, and then 1 bridge each connected the other island to the north and south banks. And the people of Königsberg had a little puzzle they liked to talk about, the way people in any city have local curiosities and traditions. The puzzle was this: could you walk through the city, crossing each of the 7 bridges exactly once, and end up back where you started? You couldn't cross a bridge halfway and turn back. You couldn't skip a bridge. Every bridge, exactly once, and return to your starting point. People had tried, of course. They'd trace routes on maps, walk them in person, argue about it over drinks. Nobody could find a route that worked, but nobody could prove it was impossible either. It was just one of those nagging little problems. And somehow, it made its way to Euler, who was living in St. Petersburg at the time, working at the Russian Academy of Sciences. And here's what's fascinating about what Euler did with it. He didn't solve it by trying every possible route. He didn't draw maps. He did something much more radical, something that was genuinely new. He stripped the problem down to its bare bones. He said, look, the actual layout of the city doesn't matter. The distances don't matter. The shapes of the islands don't matter. The only things that matter are the land masses and the bridges connecting them. So he replaced the entire map of Königsberg with what we'd now call a graph, just dots and lines. Each landmass became a dot, which we call a node or a vertex, and each bridge became a line connecting 2 dots, which we call an edge. And suddenly, this geographical puzzle about walking through a real city became an abstract question about tracing paths through a network of dots and lines. And then Euler proved something elegant. He showed that for such a walk to be possible, crossing every edge exactly once and returning to your starting point, every single node in the graph needs to have an even number of edges coming out of it. Think about why that makes sense. If you arrive at a node by one bridge, you have to leave by a different bridge. So bridges get used up in pairs at each node. If a node has an odd number of bridges, eventually you'll arrive there and have no unused bridge to leave by. You'll get stuck. And in the Königsberg graph, every single node had an odd number of edges. The north bank had 3 bridges, the south bank had 3, one island had 5, and the other had 3. All odd. So the walk was impossible. Not just hard to find, but provably, mathematically impossible. No one would ever find such a route, no matter how clever they were, because it simply couldn't exist. Now, you might think, okay, that's a cute puzzle, but why does it matter? And here's the thing. What Euler had done, almost without realizing the full implications, was invent a completely new way of thinking about mathematical problems. He'd shown that sometimes the important features of a situation have nothing to do with measurements or quantities, but with connections and structure. How things are linked together. The shape of the network, not the size of it. He even said as much in his paper. He wrote that this problem was related to a kind of geometry that Leibniz had once dreamed about, a geometry of position, a geometry that didn't care about magnitudes, but only about the relationships between things. Euler called it geometria situs, geometry of position, and he admitted he wasn't quite sure what to do with it beyond this one problem. But he knew it was something new, and he was right. That 1736 paper on the Königsberg bridges is now considered the founding document of two fields: graph theory, which is the study of networks, and topology, the study of spatial properties that are preserved under continuous deformation. Euler had cracked open a door, and behind it was an entirely new continent of mathematics. He just didn't know how big it was yet. But Euler wasn't done contributing to this story. A few years later, in 1750, he discovered something else, something that seems completely unrelated to bridges, but is actually deeply connected in ways that would take mathematicians another century to fully understand. He was studying polyhedra, three-dimensional shapes with flat faces, straight edges, and sharp vertices. Think of a cube, or a pyramid, or a dodecahedron, those beautiful 12-sided shapes that look like fancy dice. And Euler noticed a pattern. If you count the number of vertices, subtract the number of edges, and add the number of faces, you always get the same answer. Always. For a cube, 8 vertices minus 12 edges plus 6 faces equals 2. For a tetrahedron, the simplest pyramid, 4 vertices minus 6 edges plus 4 faces equals 2. For a dodecahedron, 20 vertices minus 30 edges plus 12 faces equals 2. It's always 2. Every single convex polyhedron he checked gave the same result. This is Euler's formula for polyhedra, and it's usually written as V minus E plus F equals 2. And it's one of those results that feels almost magical when you first encounter it. Why should this particular combination of counting always give you the number 2? What's special about 2? And what Euler had stumbled onto, though he didn't have the language for it yet, was a topological invariant, a number that captures something fundamental about the shape of an object, something that doesn't change when you deform it. Because here's the key insight, and this is where it starts connecting back to that stretchy, bendy, no rulers allowed philosophy of topology. If you imagine inflating a cube like a balloon, smoothly rounding out all the edges and corners until it becomes a sphere, the number V minus E plus F doesn't change. It's still 2. That number is telling you something about the sphereness of the shape, something about the fact that it has no holes in it, that it's a simple closed surface. And if you did the same calculation for a shape with a hole in it, like a torus, like that donut, like that coffee mug, you'd get a different number. You'd get 0. The number changes when the fundamental topology changes. Euler didn't fully understand this. He proved his formula for convex polyhedra, but he didn't have the conceptual framework to see it as a statement about surfaces and their topology. That understanding would come later, built by other mathematicians standing on his shoulders. But the formula was there, waiting, like a fossil embedded in rock that nobody quite knew how to excavate yet. And this is something I find really beautiful about the history of mathematics in general, and topology in particular. Ideas appear before the framework to understand them exists. Someone notices a pattern, proves a theorem, solves a puzzle, and only decades or centuries later does someone else come along and say, "Oh, that thing you found?" It's actually a special case of something much bigger and much deeper. Euler's bridge problem and his polyhedron formula sat there for a long time, two isolated gems, before anyone realized they were both facets of the same diamond. So after Euler, there's a gap. Not a complete gap. Mathematicians kept working on related problems throughout the late 1700s and early 1800s, but topology as a coherent field didn't really exist yet. It was more like scattered observations, individual results that didn't have a home. The next major figure to push things forward was someone who might surprise you, because he's much more famous for other things. Carl Friedrich Gauss, often called the Prince of Mathematicians, born in 1777 in Brunswick, Germany. Gauss was one of those terrifying prodigies. He supposedly corrected an error in his father's arithmetic when he was 3 years old, and by the time he was a teenager, he was making discoveries that would have been career-defining achievements for anyone else. But among his many, many contributions, Gauss spent a lot of time thinking about curves and surfaces, and he developed ideas that would become essential building blocks for topology. One of the things Gauss was deeply interested in was the concept of curvature, how a surface bends and curves at each point. And he proved something remarkable, something now called the theorema egregium, which is Latin for remarkable theorem. And honestly, the fact that Gauss himself thought it was remarkable enough to call it that should tell you something, because the man was not easily impressed. What the theorem says is that the curvature of a surface is an intrinsic property. It doesn't depend on how the surface is embedded in space. It only depends on measurements you can make while staying on the surface itself. Imagine a tiny ant living on a surface. The ant can measure distances along the surface. It can measure angles. It can detect whether the surface curves. And Gauss showed that the curvature the ant measures is a real intrinsic feature of the surface. It doesn't change if you bend the surface without stretching it. You can roll a flat piece of paper into a cylinder, and the intrinsic curvature stays zero because you haven't stretched the paper. But you can't flatten a sphere without distorting it, because a sphere has genuine intrinsic curvature that can't be removed by bending alone. That's why every flat map of the Earth is distorted. It's not a failure of cartography. It's a mathematical certainty. Now, Gauss's work on curvature isn't topology in the modern sense. It's more properly called differential geometry. But it laid crucial groundwork because it got mathematicians thinking about the intrinsic properties of surfaces, properties that belong to the surface itself, independent of how it sits in space. And that's a deeply topological way of thinking. It's the same instinct that says a coffee mug and a donut are the same. Forget about the external appearance. Forget about the embedding. Focus on what's intrinsically true about the shape. Gauss also spent time thinking about knots, which would eventually become a whole subfield of topology. He sketched out some early ideas about how to classify knots mathematically, though he never published a full theory. And he had a student, a quiet, brilliant, somewhat fragile young man, who would take these ideas about surfaces and curvature and push them into territory that Gauss himself might not have imagined. That student's name was Bernhard Riemann, and what he did in a single lecture in 1854 would reshape the entire landscape of mathematics. Riemann was only 27 years old. He was shy, he struggled with anxiety, and public speaking terrified him. And yet the lecture he delivered that day, his Habilitationsvortrag, the qualifying lecture required to become a university lecturer in Germany, is one of the most important mathematical presentations ever given. Gauss was in the audience. He was old by then, in the last year of his life. and by all accounts, he was visibly moved by what he heard. Here's what Riemann did. He took Gauss's idea of intrinsic geometry on two-dimensional surfaces and asked a deceptively simple question. Why stop at 2 dimensions? Why can't we think about curved spaces with 3 dimensions, or 4, or any number of dimensions? And not just spaces that sit inside some larger space, spaces that exist on their own terms, defined entirely by their intrinsic properties. Riemann called these manifolds, from the German word Mannigfaltigkeit, which roughly translates to many-foldedness. And with that single concept, he cracked open a door that mathematics is still walking through today. Think about what that means. Before Riemann, when mathematicians talked about geometry, they were essentially talking about flat Euclidean space, the kind of space you learned about in school, with its parallel lines and right angles and everything behaving nicely. Or they were talking about surfaces embedded in that space, like Gauss's curved surfaces sitting inside ordinary, three-dimensional Euclidean space. Riemann said, no, a space doesn't need to live inside anything else. You can define a space purely by describing how distances work within it. You specify what mathematicians call a metric, a rule that tells you the distance between any two nearby points. And that metric defines the geometry. The space is its own thing. It doesn't need a container. And here's what's really beautiful about this. Riemann didn't just generalize to higher dimensions for the fun of it. He showed that these higher dimensional manifolds could be curved in all sorts of ways. A two-dimensional surface can be curved like a sphere, or curved like a saddle, or flat like a plane. A three-dimensional manifold can do all of those things and more, curving differently in different directions, the curvature varying from point to point. Riemann gave mathematicians the tools to describe all of this precisely, using what we now call the Riemann curvature tensor. And this isn't just abstract mathematics. 60 years later, Einstein would use exactly this framework to build general relativity, describing gravity not as a force, but as the curvature of a four-dimensional spacetime manifold. The geometry of the universe itself is Riemannian geometry. When people say that massive objects bend space, they're talking about Riemann's manifolds. But for our story, the story of topology, what matters most about Riemann isn't the curvature. It's the manifold concept itself. Because once you have the idea that spaces can be abstract objects defined by their own internal structure, you can start asking topological questions about them. What shape is this manifold? How many holes does it have? Can it be continuously deformed into some other manifold? Is it finite or infinite? Does it have edges or does it close up on itself? These are questions about the global structure of the space, and they don't depend on the specific metric you chose. You could change the metric, stretch the manifold, warp it, make some parts more curved than others, and the topological features would remain the same. The number of holes doesn't change when you stretch. The overall connectedness doesn't change. These are the deep, invariant properties, the ones that topology cares about. Riemann himself explored this in a stunning way with his work on what we now call Riemann surfaces. These came out of his study of complex analysis, the mathematics of functions involving complex numbers. Now, complex numbers are numbers that have two parts, a real part and an imaginary part, and functions of complex numbers can behave in wonderfully strange ways. One of the strangest is that many complex functions are what mathematicians call multi-valued. Take the square root function. The square root of 4 is 2, right? But it's also -2. Both are valid square roots. For real numbers, we just pick the positive one and move on. But in complex analysis, you can't always do that so cleanly. As you move around in the complex plane, following a path, the function can smoothly shift from one value to another, and when you come back to where you started, you might be on a different branch of the function. Riemann's insight was to take these multiple branches and stitch them together into a single surface, a surface where the function is genuinely single-valued, because each branch lives on its own sheet of the surface, and the sheets are connected at special points called branch points. Picture taking two copies of a flat sheet, cutting each one along a line, and then gluing the top edge of the cut on one sheet to the bottom edge of the cut on the other sheet, and vice versa. You get this twisted, layered surface where you can smoothly walk from one sheet to the other. That's a Riemann surface. And the topology of that surface, how many holes it has, how the sheets connect, tells you deep things about the behavior of the complex function. This was revolutionary. Riemann was saying that to understand a function, you should understand the shape of the space it naturally lives on. The algebra and the topology are intertwined, and the genus of the Riemann surface, that's the technical term for the number of holes, turns out to control all sorts of properties of the function. A Riemann surface with no holes is topologically a sphere. One with one hole is a torus, 2 holes, 3 holes, and so on. And remember Euler's formula, the one about vertices minus edges plus faces? The Euler characteristic of a surface with g holes is 2 minus 2 times g. So a sphere has Euler characteristic 2. A torus has 0. A 2-holed surface has -2. Riemann connected these topological invariants directly to the analytic properties of complex functions. The topology determines the mathematics. That's a profound idea, and it's one that keeps showing up throughout our story. Riemann died young. He was only 39, taken by tuberculosis in 1866. He left behind a relatively small body of published work, but almost every piece of it opened up entirely new fields. His ideas about manifolds, about Riemann surfaces, about the connection between topology and analysis, these would take decades for other mathematicians to fully absorb and develop. And in a way, that's a recurring pattern in the history of topology. Someone has an insight that's ahead of its time, and then the mathematical community has to slowly build the tools and language to make that insight rigorous and extend it. So let's talk about what happened after Riemann, because this is where topology starts to become a subject in its own right, with its own name and its own community of practitioners. And the person who did more than anyone else to make that happen was a French mathematician named Henri Poincaré. Poincaré is one of those figures who's hard to overstate. He was the last great universalist, the last mathematician who could claim to work productively across essentially all branches of mathematics and mathematical physics. He published over 500 papers and 30 books. He contributed to number theory, algebraic geometry, celestial mechanics, electromagnetic theory, the philosophy of science. He nearly scooped Einstein on special relativity. And starting in the 1890s, he essentially invented algebraic topology. Here's the thing about Poincaré. He thought visually. He thought in terms of shapes and spaces and transformations. He once described how his mathematical ideas came to him, not through careful logical deduction, but through sudden flashes of intuition, often at unexpected moments. He famously described stepping onto a bus in Coutances and suddenly realizing, with complete certainty, that a set of mathematical transformations he'd been studying were related to non-Euclidean geometry. The idea arrived whole, unbidden, and he simply knew it was correct. He sat down and verified it later, but the insight came first, in a flash. That visual, intuitive style shaped how Poincaré approached topology. In 1895, he published a landmark paper called Analysis Situs, that's Latin for analysis of position, echoing Leibniz's old phrase that Euler had drawn on. In this paper and a series of supplements that followed over the next decade, Poincaré laid out the foundations of what we now call algebraic topology. And his central insight was this: you can study the shape of a space by associating algebraic objects to it, groups, numbers, polynomials, that capture the space's topological features. If two spaces have different algebraic invariants, they must be topologically different. They can't be deformed into each other. The most intuitive of these invariants is something called the fundamental group, and it's such a beautiful idea that it's worth taking a moment to really sit with it. Imagine you're standing at a point on some surface or space. You take a walk, any walk you like, but you have to end up back where you started. You've traced out a loop. Now, the question is, can that loop be continuously shrunk down to a point? On a flat plane, the answer is always yes. Any loop you draw can be pulled tight until it's just a dot. But on a torus, a donut, some loops can't be shrunk. Think about a rubber band wrapped around the hole of the donut. You can slide it around, you can wiggle it, but you cannot shrink it to a point without cutting it or lifting it off the surface. It's caught around the hole. Poincaré's fundamental group captures exactly this. You take all possible loops starting and ending at your chosen point, and you consider two loops to be the same if one can be continuously deformed into the other. Then you define a way to combine loops. You walk around one loop, then walk around another, and the combination is a new loop. This gives you a group, an algebraic structure, and that group encodes information about the holes in your space. For a sphere, the fundamental group is trivial. Every loop can be shrunk, so there's essentially only one type of loop. For a torus, the fundamental group is more interesting. It's generated by two basic loops, one going around the hole and one going through it, and they combine in specific ways. And here's where Poincaré asked a question that would haunt mathematics for over a century. He knew that a two-dimensional sphere has a trivial fundamental group. Every loop on a sphere can be shrunk to a point. And he knew the converse was true in 2 dimensions. If every loop on a closed two-dimensional surface can be shrunk to a point, then that surface must be a sphere. So he asked, is the same thing true in 3 dimensions? If you have a closed 3-dimensional manifold, and every loop in it can be shrunk to a point, must it be a 3-dimensional sphere? That question, posed almost as an afterthought in a supplement to Analysis Situs published in 1904, became known as the Poincaré Conjecture, and it would remain unsolved for 99 years, resisting the efforts of the greatest topologists of the 20th century, until a reclusive Russian mathematician named Grigory Perelman finally proved it in 2003, using methods that Poincaré could never have imagined. But we'll come back to that story later, because it's one of the most remarkable tales in all of mathematics. What matters right now is what Poincaré built. He didn't just define the fundamental group, he developed a whole toolkit. He introduced homology, a way of detecting holes of different dimensions by looking at cycles and boundaries. He defined the Betti numbers, which count the number of independent holes of each dimension. He proved a duality theorem for closed manifolds, now called Poincaré duality. which reveals a beautiful symmetry in the topology of these spaces. And he did all of this with a combination of geometric intuition and algebraic formalism that set the template for how topology would be practiced for the next century. But Poincaré's work was also, by modern standards, not entirely rigorous. He relied heavily on intuition, and some of his arguments had gaps. He was working in a period when the foundations of topology, even the precise definition of what a space was, hadn't been fully nailed down. And that foundational work was happening simultaneously, driven by a different set of concerns entirely. While Poincaré was studying manifolds and algebraic invariance, other mathematicians were grappling with a more basic question. What exactly is a topological space? What are the minimal ingredients you need to talk about continuity, about nearness, about convergence, without any reference to distance or coordinates at all? And the answers to those questions were coming from an unexpected direction, from the study of real analysis and set theory, the deep investigation of what functions actually do and how infinite collections actually behave. See, by the late 1800s, mathematics was going through something of an identity crisis. People like Weierstrass and Dedekind and Cantor were digging into the foundations of calculus, trying to make rigorous all those notions that Newton and Leibniz had used so freely: limits, continuity, convergence. And what they kept bumping into was the realization that to talk about any of these things precisely, you needed to be very careful about what you meant by closeness. What does it mean for a sequence of points to converge? What does it mean for a function to be continuous? In ordinary calculus, you define these things using distance, epsilon delta arguments, where you say two points are close if the distance between them is less than some small number. But here's the thing. Distance, it turns out, is more structure than you actually need. You can strip away the notion of distance entirely and still preserve the essential idea of continuity, of openness, of what it means for points to cluster together. And the person who saw this most clearly was Felix Hausdorff. Hausdorff was a German mathematician born in 1868 in Breslau, which is now Wrocław in Poland. And his story is one of those that reminds you how intertwined mathematics is with the larger currents of history, often in the most tragic ways. But we'll get to that. First, let's talk about what he built, because it was genuinely revolutionary. In 1914, Hausdorff published a book called Grundzüge der Mengenlehre, Foundations of Set Theory. And in this book, he did something that might sound dry on the surface, but was actually a profound act of abstraction. He defined what we now call a topological space. The idea goes like this: forget about distance, forget about coordinates, forget about curves and surfaces and manifolds for a moment. Start with just a set, a collection of points, any collection at all. Now, designate certain subsets of that collection as open. That's it. You just declare which subsets are open, subject to a few simple rules. The empty set and the whole set are both open. The intersection of any two open sets is open. The union of any collection of open sets, even infinitely many, is open. That's the whole definition. A topological space is a set together with a collection of subsets satisfying those three axioms. And you might be thinking, that's absurdly minimal. What can you possibly do with just that? But here's what's wild. You can do almost everything. With just that structure, you can define what it means for a function to be continuous. A function between two topological spaces is continuous if the pre-image of every open set is open. You can define what it means for a sequence to converge. what it means for a set to be connected, what it means for a space to be compact. All the essential concepts of analysis and geometry can be reformulated in this incredibly spare language of open sets. Think about what that means. Poincaré was studying manifolds, these beautiful, smooth, curved spaces, and developing powerful tools to classify them. But Hausdorff was working at a deeper level, asking, what is the bare minimum of structure that makes topology possible at all? And the answer turned out to be shockingly little. You don't need smoothness. You don't need curvature. You don't even need distance. You just need a notion of which sets are open. Now, Hausdorff himself added an extra condition that bears his name, the Hausdorff separation axiom, which says that any two distinct points can be separated by disjoint open sets. This rules out some pathological examples and ensures that limits, when they exist, are unique. Most spaces that arise naturally in mathematics and physics satisfy this condition, so it's a reasonable thing to ask for. But the general framework allows you to study spaces that don't satisfy it too, and that flexibility turned out to be important. Here's a good way to think about why this matters. Remember how Riemann defined manifolds? He said a manifold is a space that locally looks like ordinary Euclidean space. You can set up coordinates in small patches, and where patches overlap, the coordinate changes are smooth. That's a very specific and structured kind of space. Hausdorff's topological space is far more general. A manifold is a topological space with extra structure layered on top. So what Hausdorff did was identify the bottom layer, the foundation on which everything else is built. And this wasn't just an exercise in abstraction for its own sake. Having the right foundations matters enormously. It's like the difference between building a house on bedrock versus building it on sand. Once you have a clean, precise definition of topological space, you can state theorems with full generality. You can identify exactly which properties of a space are needed for a given result. And you can avoid the kind of gaps and ambiguities that had plagued earlier work, including, frankly, some of Poincaré's. But I want to come back to Hausdorff, the person, for a moment, because his story deserves to be told. He wasn't just a mathematician. Under the pseudonym Paul Mongré, he published literary and philosophical works, essays, a book of aphorisms, even a play. He was a cultured, deeply thoughtful man who moved in intellectual circles that included figures like Nietzsche's sister, though his relationship with Nietzschean philosophy was complex and critical rather than worshipful. He was, by all accounts, a gentle and principled person. And when the Nazis came to power in 1933, his life was systematically destroyed. He was Jewish. He was forced out of his professorship at the University of Bonn. His work was dismissed. His world contracted. And in January 1942, when he and his wife's sister learned that they were about to be sent to a concentration camp, they took their own lives together. He was 73 years old. In his suicide note, he wrote to a friend, asking him to take care of their affairs with a calm dignity that is almost unbearable to read. The mathematics he left behind, the framework of topological spaces, his contributions to set theory, measure theory, and more, endures as one of the great intellectual achievements of the 20th century. But the cost of what was lost, the work he might still have done, the students he might have taught, that's incalculable. So, Hausdorff gave topology its foundations. But foundations alone don't build the building. What happened next was a period of extraordinary construction, roughly the 1920s through the 1940s. when mathematicians took the tools that Poincaré had sketched and the framework that Hausdorff had provided and built them into a rigorous, powerful, interconnected theory. And the key figures in this period form a kind of constellation. Emmy Noether, Leopold Vietoris, Heinz Hopf, Edward Czech, Witold Hurowicz, Solomon Lefschetz, and others. Let's talk about Emmy Noether, because her influence on topology is one of those things that often gets overlooked. You might know Noether from physics. Noether's theorem, the one that connects symmetries to conservation laws, is one of the most profound results in all of theoretical physics. But Noether was first and foremost an algebraist, and her algebraic perspective transformed topology in the 1920s and 1930s. Here's what she did. Remember Poincaré's homology, his way of detecting holes by looking at cycles and boundaries. Poincaré thought of homology in fairly geometric terms, working with specific chains and cycles. Noether looked at the same ideas and saw algebra. She realized that the cycles form a group, the boundaries form a subgroup, and the thing you really want to study is the quotient, the group of cycles modulo boundaries. This is the homology group. Now that might sound like a small repackaging, just putting old wine in new bottles, but it was far more than that. By recognizing homology as a group, an algebraic object with its own structure, Noether opened the door to using all the powerful machinery of abstract algebra to study topological problems. You could talk about homomorphisms between homology groups, exact sequences, direct sums, torsion. Suddenly, topology had an algebraic engine under the hood, and that engine was enormously powerful. And this algebraic turn didn't just affect homology. It rippled through the whole subject. The fundamental group that Poincaré had defined, that's an algebraic object too. A group, specifically. And mathematicians began to study it with algebraic tools, classifying spaces by the algebraic properties of their fundamental groups. Higher homotopy groups were introduced by Hurowicz in the 1930s, extending Poincaré's fundamental group to higher dimensions. Instead of just looking at loops, you look at how spheres of various dimensions can be mapped into your space, and cohomology, a kind of dual theory to homology, was developed by Czech, Alexander, and others, giving topologists yet another algebraic invariant to work with. This whole program, using algebraic structures to study topological spaces, became known as algebraic topology, and by the 1940s it was one of the most active and exciting areas of mathematics. The key insight, the one that drove everything, was this. Topology is hard. Spaces are squishy and deformable and hard to get a grip on directly. But algebra is rigid and structured and computable. So if you can build a bridge from topology to algebra, if you can associate algebraic objects to topological spaces in a way that respects the topological structure, then you can translate hard topological questions into more tractable algebraic ones. And here's the beautiful thing about how these algebraic invariants work. They're functorial, a word that comes from category theory, which was itself being developed during this period by Eilenberg and Mac Lane, partly in response to the needs of algebraic topology. What functorial means, in plain language, is that the bridge between topology and algebra isn't just a static dictionary, it's a dynamic correspondence. When you have a continuous map between two topological spaces, it automatically induces a homomorphism between their algebraic invariants. The algebra doesn't just label the spaces, it tracks the relationships between them, and that makes it incredibly powerful for proving things. Let me give you a taste of what this machinery can do, because one of the most famous applications is something you've probably heard of even if you didn't know it was topology. It's the Brouwer fixed-point theorem, proved by L.E.J. Brouwer in 1911, though it was later given much cleaner proofs using the algebraic tools we've been talking about. The theorem says this: take a disk, a filled-in circle, and apply any continuous function that maps the disk to itself. Then there must be at least one point that doesn't move. A fixed point. Always. No matter what the function is, as long as it's continuous. Think about that concretely. Take a cup of coffee and stir it any way you like, as long as the stirring is continuous. No teleporting drops of coffee from one place to another. When you're done, at least one molecule of coffee is in exactly the same position it started in. That's the Brewer fixed point theorem, and it generalizes to higher dimensions too. It works for balls in any dimension. Now, the proof using algebraic topology is elegant. You assume there's no fixed point and derive a contradiction. If no point is fixed, you can construct a continuous map from the disk to its boundary, its edge, that keeps boundary points where they are. This is called a retraction. But then you look at what this retraction does to the homology groups, and you find that it forces a certain algebraic relationship that's impossible. The algebra says no. And because the algebra faithfully reflects the topology, no means no. There's no such retraction, so there must be a fixed point. This is the paradigm of algebraic topology in action. You take a geometric question, translate it into algebra, and let the algebra do the heavy lifting. And throughout the middle decades of the 20th century, this approach yielded one spectacular result after another. But perhaps the most dramatic story from this era, the one that showed just how deep and strange topology could get, involves the higher homotopy groups of spheres, a problem that sounds almost too simple to be interesting. You've got spheres. You've got maps between spheres. What could be so complicated? But this is where topology reveals a depth that nobody expected, a labyrinth hiding inside the most basic shapes imaginable. And people spent decades, are still spending decades, trying to map it out. So let's set this up properly. You already know what a sphere is, at least intuitively. The one-dimensional sphere, which topologists call S1, is just a circle. The two-dimensional sphere, S2, is the surface of a ball, the thing you picture when someone says sphere. S3 is harder to visualize because it lives naturally in four-dimensional space, but it's the same idea extended one dimension up, and so on for S4, S5, as high as you want to go. Now, the fundamental group that Poincaré defined, that's about loops. You take loops on a space and ask which ones can be shrunk to a point and which ones can't. That's the first homotopy group, usually written pi1. But Hirowich and others realized you could generalize this. Instead of mapping circles into your space, you map higher dimensional spheres. Pi2 of a space asks, take all the ways you can wrap a two-dimensional sphere into your space. Which of those wrappings can be continuously deformed to a single point, and which can't? Pi3 asks the same thing, but with three-dimensional spheres, and so on. Here's where you might expect things to be straightforward. If you're mapping a low-dimensional sphere into a high-dimensional one, there should be plenty of room, right? You should be able to unwrap any mapping. And that's exactly correct. If you map S1, a circle, into S2, the ordinary sphere, you can always shrink that circle to a point on the sphere's surface. There's nothing for it to get tangled around. Pi1 of S2 is trivial. It's zero, topologically speaking. And more generally, pi k of Sn is zero whenever k is less than n. Lower dimensional spheres mapped into higher dimensional ones can always be untangled. Makes sense. And when k equals n, when you're mapping a sphere into a sphere of the same dimension, you get something clean and beautiful. Pi n of Sn is the integers z. The maps are classified by their degree, which is essentially how many times you wrap one sphere around the other. Wrap it once, that's degree 1. Wrap it twice, degree 2. Wrap it backwards, degree -1. Don't wrap it at all, degree 0. This is satisfying, elegant, and exactly what you'd hope for. But here's where the story takes a turn that nobody saw coming. What about pi minus k of s minus n, when k is bigger than n? When you're mapping a higher dimensional sphere into a lower dimensional one? Your first instinct might be that all such maps should be trivial. After all, you're trying to stuff something big into something small. Surely you can always simplify it, collapse it down, deform it to a constant map. And for a long time, people assumed something like that might be true, or at least that the answer would be simple. Then, in 1931, Heinz Hopf discovered something astonishing. Hopf was a German-born mathematician working in Zurich, a quiet and deeply geometric thinker. He was the kind of mathematician who could see shapes in his mind with extraordinary clarity, and what he found was a map from S3, the three-dimensional sphere, down to S2, the ordinary sphere, that could not be deformed to a constant map. It was a genuinely non-trivial wrapping of a higher dimensional sphere around a lower dimensional one. This map is now called the Hopf fibration, and it's one of the most beautiful objects in all of mathematics. Let me try to give you a feel for what it looks like, even though it lives in dimensions that are hard to picture directly. Think of S3 sitting in four-dimensional space. The Hopf fibration assigns to every point on S3 a point on S2. And if you ask, which points in S3 get sent to a particular point on S2? If you look at the preimage of any single point, you get a circle. Every point on the two-sphere has a full circle of points in the three-sphere mapping to it. So S3 is decomposed into circles, one for every point of S2, and these circles are linked. Every circle is linked with every other circle, like links in a chain, but in a very specific symmetric way. The whole three-sphere is filled with these interlinked circles, fibers, all twisting around each other in a pattern of extraordinary elegance. And the key point, the topological point, is that this map is not homotopic to a constant. You can't continuously deform it to a map that sends all of S3 to a single point on S2. The linking of those fibers is a topological obstruction. It's real. It's there, and it means that pi3 of S2 is non-trivial. In fact, pi3 of S2 is the integers. The Hopf map generates an infinite family of maps, classified by how many times the fibers wind around each other. Think about what that means. A three-dimensional sphere can wrap around a two-dimensional sphere in infinitely many essentially different ways. That's not at all obvious. That's genuinely surprising. And it was just the beginning. Because once people started computing these higher homotopy groups of spheres, pi4 of S2, pi5 of S3, pi7 of S4, and on, the results were wild. There's no simple pattern. Some of these groups are zero, some are the integers, some are finite cyclic groups of various orders, some are products of cyclic groups. The whole table of homotopy groups of spheres looks, frankly, chaotic. It's one of the great mysteries of mathematics that such a fundamental question, how can spheres wrap around other spheres, leads to such an irregular, unpredictable landscape. And this isn't just abstract puzzle-making. These homotopy groups connect to physics, to the classification of fiber bundles, to the structure of gauge theories. The Hopf fibration itself shows up in quantum mechanics, in the geometry of spin, in the behavior of magnetic monopoles. When a physicist talks about the topology of a field configuration, they're often talking about exactly these kinds of maps between spheres. But let's stay with the mathematical story for a moment, because the effort to compute homotopy groups of spheres drove some of the most powerful developments in 20th century topology. One of the key figures here is Jean-Pierre Serre, a French mathematician who was, and still is, remarkably, as of the early 21st century, one of the most brilliant mathematicians alive. In the early 1950s, when Serre was barely in his mid-20s, he developed a technique called the Serre spectral sequence that allowed him to compute homotopy groups that had been completely out of reach. Now, spectral sequences are notoriously difficult objects. There's a famous joke among mathematicians that spectral sequences are the most powerful tool that nobody understands. They're like elaborate bookkeeping machines. You feed in information about a space that's been decomposed into pieces, and through a series of successive approximations, each one refining the last, you extract topological information about the whole. Each page of the spectral sequence gives you a better approximation, and under the right conditions, the process converges to the answer you want. It's intricate, technical, and when it works, almost magical. What Serre showed, among many other things, was that the homotopy groups of spheres are all finitely generated, and that in a certain sense, the only place where infinite groups appear is in the cases you'd expect. Pn of Sn being the integers, and P4 n-1 of S2n, which also has an integer component, related to generalizations of the Hopf fibration. Everything else is finite, complicated, unpredictable, but finite. For this work, Serre became the youngest ever recipient of the Fields Medal in 1954 at age 27. He remains one of the most decorated mathematicians in history, and Serre's work opened the floodgates. Throughout the 1950s and 1960s, algebraic topology experienced a golden age. The tools became more and more sophisticated, not just spectral sequences, but cohomology operations, K-theory, cobordism theory. Each one was a new lens for seeing topological structure that had been invisible before. Let me tell you about one of the most consequential developments from this era, because it connects back to something very concrete: the question of how many different smooth structures you can put on a sphere. This sounds like it should have an obvious answer. A sphere is a sphere, right? How many ways can there be to do calculus on it? You'd think just one. And for ordinary spheres in dimensions 1, 2, 3, 5, and 6, that's correct. There's exactly one smooth structure, up to the appropriate notion of equivalence. But in 1956, John Milnor, another towering figure, an American mathematician at Princeton, proved something that stunned the mathematical world. He showed that the seven-dimensional sphere, S7, admits exotic smooth structures. Specifically, he constructed smooth manifolds that are homeomorphic to S7. Topologically, they are seven-dimensional spheres. But they are not diffeomorphic to the standard S7. They're the same topologically but different as smooth objects. You can set up calculus on them, but the calculus works differently than it does on the standard sphere. It's as if you have two globes that look identical, that you can deform one into the other continuously, but when you try to do it smoothly, without any kinks or corners in the deformation, you can't. Milnor eventually showed there are exactly 28 distinct smooth structures on S7, 28 versions of the seven-dimensional sphere that are all the same topologically, but all different smoothly. These are called exotic spheres, and their discovery was a thunderbolt. It revealed that the relationship between topology and smooth structure is far more subtle than anyone had imagined. The tools Milnor used to detect these exotic structures drew heavily on the homotopy theory and cobordism theory that had been developed in the preceding years. The algebraic machinery was essential. And here's something that connects this to an even bigger story. The question of exotic structures isn't just about spheres. You can ask the same question about any manifold. And in dimension 4, the dimension most relevant to physics, since we live in a four-dimensional space-time, the situation is the strangest of all. In the early 1980s, Simon Donaldson, a young British mathematician, used ideas from gauge theory, actual physics, Yang-Mills theory, to probe the smooth topology of four-dimensional manifolds, and what he found was genuinely shocking. Donaldson was barely into his 20s. He was a graduate student at Oxford, working under Michael Atiyah, one of the most influential mathematicians of the 20th century. And what Donaldson did was take the Yang-Mills equations, which physicists had been using to describe the behavior of fundamental forces, the strong force, the weak force, electromagnetism, and he turned them into a tool for pure mathematics. He used solutions of these equations, called instantons, to extract new invariants of four-dimensional manifolds, and these invariants could distinguish between smooth structures in ways that purely topological methods couldn't. Let's slow down and appreciate what's happening here, because it's one of those moments where the boundaries between mathematics and physics dissolve in the most beautiful way. Yang-Mills theory was developed in the 1950s by Chen-Ning Yang and Robert Mills to describe gauge fields, the mathematical objects that mediate forces between particles. The equations describe how these fields curve and twist over space-time. Now, space-time in general relativity is a four-dimensional manifold. So when Donaldson looked at these equations, not as a physicist trying to predict particle behavior, but as a mathematician trying to understand the topology of four manifolds, he was essentially asking, what does the space of all solutions to these equations tell me about the shape of the underlying manifold? And the answer turned out to be an enormous amount. In 1983, Donaldson proved a theorem that placed severe restrictions on which four-dimensional manifolds can carry a smooth structure. Specifically, he showed that if a compact, simply connected smooth four-manifold has a definite intersection form. Don't worry too much about the technical details, but the intersection form is an algebraic object that encodes how two-dimensional surfaces sitting inside the four-manifold intersect each other. Then that intersection form must be diagonalizable. It must be equivalent to a particularly simple, standard form. Now this might sound abstract, but here's the kicker. Topologically, Michael Friedman had just shown, around the same time, in 1982, that there exist four manifolds whose intersection forms are not diagonalizable. Friedman proved that these exotic topological four manifolds exist. So Donaldson's result meant that these topological manifolds that Friedman had constructed cannot be given any smooth structure at all, or if they can, the smooth structure forces the intersection form to change character. The two results together, Friedman's topological classification and Donaldson's smooth obstruction, revealed that dimension 4 is special. It's the one dimension where the gap between topology and smooth structure is the widest, the most wild, the most untamed, and it gets even stranger. Think about this. In every other dimension, 2, 3, 5, 6, 7, and up, the number of exotic smooth structures on a given manifold is either 0 or finite. Milnor found 28 on the 7-sphere, and similar finite counts appear in other high dimensions. In dimensions 1, 2, and 3, smooth structures are unique. There's only one way to make things smooth. But in dimension 4, the situation explodes. Thanks to work by Donaldson and later by Robert Gompf and others, it was shown that ordinary four-dimensional Euclidean space, just flat, plain, boring R4, the space you'd use for coordinates in physics, admits uncountably many exotic smooth structures. Uncountably many. Not 28, not 1,000, an infinity so large it can't even be listed. There are more exotic smooth structures on R4 than there are rational numbers, more than there are integers. The same topological space, the simplest possible four-dimensional space, can be made smooth in ways that are genuinely, detectably different from each other. And there are more of these ways than you could ever catalog. Nobody expected this. Nobody. It's one of those results that makes you sit back and wonder what's really going on in 4 dimensions. And the fact that 4 is the dimension of space-time, the dimension we actually inhabit, has led to all kinds of speculation about whether these exotic, smooth structures might have physical significance. Could the universe have chosen one smooth structure over another? Would physics look different on an exotic R4? These questions are still open. Nobody knows. Donaldson received the Fields Medal in 1986 for this work, at the age of 29. Friedman had received his in the same year. 2 Fields Medals, awarded for results that together painted this extraordinary picture of 4-dimensional topology. And the tools they used couldn't have been more different. Friedman's proof was a tour de force of geometric topology, involving infinite constructions called caisson handles, and an incredibly delicate limiting argument, while Donaldson's was rooted in the analysis of partial differential equations from physics. 2 completely different worlds of mathematics converging on the same dimension and revealing its secrets from opposite sides. Now, I want to come back to something we touched on earlier because this is where one of the great stories of 20th century mathematics reaches its climax. Remember Poincaré? Remember how he formulated that conjecture back around 1904? The question of whether every simply connected, closed 3-dimensional manifold is homeomorphic to the 3-sphere? He'd been building algebraic topology from the ground up, defining the fundamental group, working out homology, and he realized that having all the same algebraic invariance as the sphere wasn't quite enough to guarantee you were the sphere. So he posed the question, is simple connectivity, having a trivial fundamental group, sufficient in dimension 3? For nearly a century, this problem resisted every attack. It became one of the most famous unsolved problems in all of mathematics. People tried everything. They tried to prove it directly. They tried to find counterexamples. They developed entirely new branches of mathematics, partly motivated by the desire to crack it. And one by one, the analogous conjectures in higher dimensions fell. Stephen Smale proved the generalized Poincaré conjecture in dimensions 5 and above in 1961. He showed that any homotopy sphere in those dimensions is homeomorphic to the standard sphere. His proof used a technique called the H-cobordism theorem, and it was beautiful, but it fundamentally relied on having enough room to maneuver, enough dimensions to push things around. Friedman's 1982 result settled the 4-dimensional case, at least topologically. But dimension 3, the original dimension Poincaré had asked about, remained stubbornly open. Here's the thing about dimension 3. It's low enough that you don't have the elbow room that Smale exploited in high dimensions. But it's high enough that you can't just draw pictures and see everything, the way you sometimes can in 2 dimensions. 3 manifolds are complicated, richly structured objects, and the Poincaré conjecture in dimension 3 seemed to require completely new ideas. Those ideas came from an unexpected direction. In the early 1980s, right around the same time Donaldson and Friedman were revolutionizing 4-dimensional topology, an American mathematician named William Thurston proposed something extraordinary. Thurston conjectured that every 3-dimensional manifold can be cut into pieces, and each piece can be given one of exactly 8 types of geometric structure. This is called the geometrization conjecture, and it's a vast generalization of the Poincaré conjecture. If geometrization is true, the Poincaré conjecture follows as a special case. Thurston's vision was that, Three manifolds, despite their complexity, have a hidden geometric order. You just have to know how to decompose them. Thurston himself proved geometrization for a large class of three manifolds, the ones called Haken manifolds, and he received the Fields Medal in 1982 for this and related work. But the full conjecture for all three manifolds remained open, and the tool that would eventually crack it wide open came from, of all places, the study of heat flow. In 1982, Richard Hamilton, an American mathematician, introduced something called the Ricci flow. The idea is deceptively simple, at least in spirit. You take a Riemannian metric on a manifold. Remember, a metric is the thing that tells you distances and angles, the thing Riemann himself dreamed up back in 1854, and you let it evolve over time, according to a differential equation that's analogous to the heat equation. The heat equation describes how temperature distributes itself evenly over time. Put a hot spot on a metal plate, and heat flows from hot regions to cold regions until the temperature is uniform everywhere. Hamilton's Ricci flow does something similar, but for curvature. It takes a manifold with lumpy, uneven curvature and smooths it out, flowing the geometry towards something more uniform. Hamilton's insight was that if you could run Ricci flow long enough on a three-manifold, the geometry would eventually settle into one of Thurston's 8 types, and you'd have geometrization. The problem was that the flow doesn't always behave nicely. Sometimes the curvature concentrates and blows up. The manifold develops singularities, pinch points where the geometry becomes infinitely sharp. Hamilton made enormous progress through the 1980s and 1990s, developing the theory of Ricci flow, understanding many types of singularities, proving the conjecture in special cases. But the general case, handling all possible singularities, eluded him. And then, in November 2002, a Russian mathematician named Grigory Perelman posted the first of 3 papers to the Archive, an online preprint server. No fanfare, no press conference, just a paper uploaded quietly that began to lay out a program for proving the full geometrization conjecture using Ricci flow with surgery. Perelman's idea was that when the flow develops a singularity, you don't give up. You perform surgery on the manifold, cutting out the singular region, capping off the resulting boundaries with standard pieces, and then restarting the flow. It's like a surgeon removing a tumor so the body can continue healing. And Perelman showed, through an extraordinarily intricate argument, that this process terminates. You only need finitely many surgeries, and eventually, the flow smooths the entire manifold into geometric pieces. The mathematical community spent several years carefully verifying Perelman's arguments. Teams of mathematicians, notably John Morgan and Gang Tian, and separately Bruce Kleiner and John Lott, and also Huidong Xiao and Xiping Zhu, wrote detailed expositions filling in every step. And by 2006, the consensus was clear. Perelman's proof was correct. The Poincaré Conjecture, after 99 years, was solved, and so was the full geometrization conjecture. What happened next is one of the most remarkable stories in the history of mathematics, and it's really about the person more than the theorem. Perelman was offered the Fields Medal in 2006. He declined it. He simply said no. He was offered the Clay Millennium Prize, $1 million, because the Poincaré Conjecture was one of the 7 Millennium Prize problems designated by the Clay Mathematics Institute in 2000, each carrying $1 million reward. He declined that too. He had withdrawn from the mathematical community, moved back in with his mother in St. Petersburg, and by all accounts, simply walked away from professional mathematics. When journalists tracked him down, he said something to the effect that the prize was irrelevant. If the proof was correct, that was what mattered, and no award could add to or subtract from that. It's hard to know what to make of Perelman's withdrawal, and I don't want to psychoanalyze someone I've never met. But there's something almost fitting about it. This problem that had obsessed mathematicians for a century, solved by someone who then decided that the solving was enough. The human drama around the proof was complicated too. There were controversies about credit, about whether certain teams had tried to claim more of the glory than they deserved, and Perelman seemed disgusted by the whole spectacle. But the mathematics itself stands, luminous and unambiguous, and what Perelman's proof really showed, at its deepest level, is something we've been circling around this whole time: the profound connection between geometry and topology. Riemann dreamed of it. Poincaré built the algebraic framework to study it. Thurston envisioned the geometric classification. Hamilton invented the analytical engine, and Perelman made it all work. The idea that you can understand the shape of a space, its topology, by flowing its geometry, by letting curvature redistribute itself the way heat does, until the space reveals its own inner structure. That's one of the most beautiful ideas in all of mathematics, that you can let a shape speak for itself, let it relax into its truest form, and then read off its identity from the geometry it settles into. It's almost biological, isn't it? Like watching a crumpled flower open in water and recognizing what species it is only after it's fully unfurled. But here's the thing. While the Poincaré Conjecture and the geometrization program were occupying center stage in three-dimensional topology, the broader world of topology was expanding in directions that would have astonished Poincaré himself. And some of those directions were reaching out of pure mathematics entirely and wrapping themselves around physics, around data, around the very way we understand information. So, let's talk about that, because this is where topology stops being something that only mathematicians care about and starts becoming something that engineers, physicists, computer scientists, and even biologists can't live without. Let's start with physics, because the connection there is the oldest and in some ways the deepest. We touched on this a little when we talked about the Hopf vibration and its relationship to quantum mechanics. But the real explosion of topology into physics happened in the 1970s and 1980s, and it happened because physicists started realizing that the fundamental forces of nature have topological structure baked into them at the deepest level. Think about it this way. In classical physics, Newton's physics, you describe the world with numbers. A particle has a position, a velocity, a mass. You write down differential equations, you solve them, you predict what happens next. And the space those numbers live in is usually just ordinary flat space, nothing topologically interesting. But when you move to quantum field theory, which is the framework for modern particle physics, the mathematical objects you're working with aren't just numbers anymore. They're fields, things like the electromagnetic field. And those fields have a structure that's described by something called a gauge theory. And gauge theories, it turns out, are fundamentally topological. Here's the intuition. In a gauge theory, you have a field defined at every point in space. But there's a redundancy built in. You can transform the field at each point by a certain symmetry operation, and the physics doesn't change. These symmetry operations form what mathematicians call a group. And the way this group of symmetries is attached to each point of space creates a structure called a fiber bundle. And fiber bundles, well, Those are exactly the kinds of objects that topologists had been studying since the 1930s and 1940s. The Hopf fibration is a fiber bundle. The whole machinery of characteristic classes, which we mentioned when talking about the algebraic topology program, was developed precisely to classify fiber bundles. So, when physicists in the 1970s started taking gauge theories seriously, and they had to, because gauge theories were giving spectacularly accurate predictions about the strong and weak nuclear forces, they found themselves using topology whether they intended to or not. The key insight was that gauge fields can have different topological types, and those types matter physically. You can't smoothly deform one into another, and the differences between them have measurable consequences. The most dramatic example is probably the magnetic monopole. In 1931, Paul Dirac had already shown that if magnetic monopoles exist, isolated north or south magnetic poles, which no one has ever observed but which aren't forbidden by the laws of physics, then electric charge must be quantized, meaning it can only come in discrete multiples of a fundamental unit. And the reason is topological. The argument hinges on the fact that if you try to define the electromagnetic potential everywhere around a monopole, you can't do it smoothly. You need at least two overlapping patches, and the way they're stitched together is classified by a topological invariant. That invariant turns out to be an integer, and that integer is what forces the charge to come in discrete chunks. It's a topological explanation for one of the most basic facts about the universe. That charge comes in units. In the 1970s, Gerard 't Hooft and Alexander Polyakov independently showed that certain gauge theories actually require monopole-like solutions, and these solutions are classified by their topological properties. Around the same time, physicists discovered instantons, which we mentioned when talking about Donaldson's work. And these are solutions to the Yang-Mills equations that are localized in both space and time, like little blips of field energy that pop into existence and vanish. The number of instantons in a given field configuration is a topological invariant, and it has physical consequences for things like the vacuum structure of quantum chromodynamics, the theory of the strong force that holds quarks together inside protons and neutrons. This is wild when you think about it. The topology of a mathematical space, something you might think is purely abstract, is directly controlling what happens inside the nucleus of every atom in your body right now. But the story gets even richer. In the 1980s, a new kind of physics emerged that was topological in an even more fundamental sense. These were called topological quantum field theories, and the person who really crystallized the idea was Edward Witten, a physicist at the Institute for Advanced Study in Princeton. Witten is one of those rare figures who operates at the boundary between physics and mathematics with equal fluency in both. In 1988, he showed that Donaldson's invariants, those things Donaldson had constructed using Yang-Mills instantons to study four-dimensional manifolds, could be reinterpreted as the output of a certain quantum field theory. In other words, the topological information that Donaldson was computing using hard analysis could also be obtained by doing a path integral in physics. Witten won the Fields Medal in 1990, one of the very few physicists ever to receive what's essentially the highest honor in mathematics. And this wasn't just a cute reinterpretation. It led to genuinely new mathematics. In the mid-1990s, Nathan Seiberg and Witten discovered a different, simpler set of equations, the Seiberg-Witten equations, that could capture much of the same topological information as Donaldson's invariants, but were far easier to work with. Overnight, proofs that had taken Donaldson dozens of pages could be done in a few. Results that had seemed out of reach suddenly became accessible. It was as if someone had handed four-dimensional topologists a telescope when they'd been squinting with the naked eye. Now, let's shift gears a little, because topology's reach extends far beyond theoretical physics. One of the most surprising developments of the last 20 or 30 years is the rise of what's called topological data analysis. And this is something that matters to engineers, to data scientists, to anyone who works with large, complex data sets. The basic idea is deceptively simple. You have a cloud of data points. Maybe they represent measurements from sensors or patient records, or the positions of stars, or the behavior of a financial market. And you want to understand the shape of that data. Not just the average or the variance, not just the clusters, but the actual shape. Are there holes in it? Loops? Voids? Is it essentially one-dimensional, like a curve? Or does it have higher dimensional structure? The tool that makes this possible is called persistent homology, and it's built directly on the algebraic topology that Poincaré, Noether, and Eilenberg developed. Here's how it works, roughly. You start with your cloud of data points, and you imagine growing a little ball around each point. When the balls of two nearby points overlap, you connect those points with an edge. As the balls keep growing, triangles form, then tetrahedra, then higher dimensional analogs. At each stage, you have a simplicial complex, exactly the kind of combinatorial object that topologists had been studying since the early 20th century. And you can compute its homology groups. The Betti numbers tell you how many connected components there are, how many loops, how many voids, and so on. But here's the clever part. As you increase the radius of those balls, the topology changes. Holes appear and then get filled in. Components merge, and persistent homology tracks which features persist across a wide range of scales, and which ones are just noise. A hole that appears at a small radius and doesn't get filled in until a much larger radius is probably a real feature of the data. A hole that appears and immediately vanishes is probably just an artifact. So you get a kind of topological fingerprint of your data, a barcode or a persistence diagram that summarizes its shape. This might sound abstract, but it's being used right now in practical engineering applications. In materials science, persistent homology has been used to analyze the structure of granular materials and porous media. Understanding the pattern of voids and channels in a material tells you about its strength, its permeability, how fluids flow through it. In neuroscience, it's been applied to the structure of neural networks in the brain, revealing organizational patterns that traditional statistical methods miss entirely. In sensor networks, it helps determine coverage, whether a collection of sensors has gaps in its monitoring area, which is fundamentally a question about holes in a topological space. In drug discovery, the shape of a molecule's binding surface can be characterized topologically, and that shape determines how it interacts with proteins in your body. There's something deeply satisfying about this arc. Euler notices something about bridges in Königsberg. Poincaré invents homology to study abstract spaces. Noether recasts it in the language of algebra. And 3 centuries after Euler, engineers are using those same ideas to analyze the shape of data from MRI scans and earthquake sensors and genomic sequences. The thread is unbroken. But topology's infiltration of the applied world doesn't stop at data analysis. There's another frontier that's arguably even more consequential, and it involves the very fabric of computation itself. In the late 1990s, a mathematician and physicist named Alexei Kitaev proposed something remarkable: a scheme for building a quantum computer that would be inherently resistant to errors, and the key to its robustness would be topology. The idea is called topological quantum computing, and to understand why it's so appealing, you need to know a little bit about the fundamental problem that plagues all quantum computers. Quantum information is extraordinarily fragile. The quantum states that encode information, the qubits, are easily disrupted by the tiniest interaction with their environment. A stray photon, a vibration, a fluctuation in temperature, and your carefully prepared quantum state decoheres, your computation is ruined. This is the decoherence problem, and it's the single biggest obstacle to building practical quantum computers. Kitaev's insight was that if you could encode quantum information not in the state of individual particles, but in the topological properties of a system of particles, then small local disturbances couldn't corrupt it, because topological properties, by definition, don't change under small continuous deformations. You'd have to make a drastic, global change to alter the topology, and random noise just doesn't do that. It's like the difference between writing a message in sand, where any breeze can erase it, and encoding it in the number of holes in a pretzel. You'd have to tear the pretzel apart to change that number. The specific particles Kitaev had in mind are called anyons, which are exotic quasi-particles that can exist in two-dimensional systems. Unlike ordinary particles, which are either fermions or bosons, anyons can have fractional statistics. When you swap two of them, the quantum state picks up a phase that's neither +1 nor -1, but something in between. And if you braid them around each other, literally move any one around another in a path that forms a braid, the quantum state of the system changes in a way that depends only on the topology of the braid, not on the exact path taken. So computation becomes braiding, and the result depends only on which strands went over which other strands, not on the precise geometry. That's topological protection at its most elegant. Now, actually building a topological quantum computer is extraordinarily difficult. The most promising candidates involve exotic states of matter called topological phases, and the search for materials and systems that host the right kind of anyons has been one of the most intense experimental efforts in condensed matter physics over the past 2 decades. Microsoft has bet heavily on this approach, investing in research labs dedicated to finding and manipulating a particular type of anyon called a Majorana zero mode, predicted to occur at the ends of certain superconducting nanowires. The experimental evidence has been tantalizing but also controversial. There have been claims of detection, retractions, and ongoing debate. As of now, no one has definitively demonstrated topological quantum computation in a laboratory. But the theoretical framework is beautiful, and it rests on ideas that trace directly back to the braid groups and homotopy theory that topologists developed in the middle of the 20th century. And this brings us to something that I think is one of the most remarkable features of topology as a discipline: its tendency to be useful long before anyone expects it to be. When Poincaré defined the fundamental group in 1895, he was thinking about the classification of abstract mathematical spaces. He certainly wasn't thinking about quantum error correction. When mathematicians in the 1920s and 1930s developed the theory of fiber bundles and characteristic classes, they weren't thinking about the strong nuclear force. When Euler proved his polyhedron formula, he wasn't thinking about sensor networks or data analysis. And yet, all of these ideas turned out to be exactly the right language for describing physical reality at its deepest level. It's as if mathematics has this uncanny ability to prepare tools decades or even centuries before physics comes knocking and says, "Hey, do you have anything that can describe a space with this particular kind of twist in it?" And the mathematicians can just gesture to a shelf and say, "Actually, yes, We worked that out in 1935. Help yourself. Eugene Wigner called this the unreasonable effectiveness of mathematics in a famous 1960 essay. He was talking about mathematics broadly, but topology might be the single best example of the phenomenon. And what's happened in the last couple of decades is that topology hasn't just continued to be useful in physics, it's become essential in an entirely new way through the discovery of topological phases of matter. This is one of those stories where the theory came first, the experiments followed, and the whole thing earned a Nobel Prize. So let's talk about it. For most of the 20th century, physicists classified phases of matter using Landau's framework of symmetry breaking. You know the basic idea, even if you've never heard Landau's name. Ice and water are the same stuff, right? Same H2O molecules. But ice has a crystalline structure. The molecules are arranged in a regular lattice, while in liquid water, they're free to move around. The transition from water to ice involves breaking a symmetry. The liquid looks the same in every direction, but the crystal picks out preferred directions. Landau's insight, developed in the 1930s, was that you could classify phase transitions by asking which symmetries get broken. It was a powerful framework, and it worked beautifully for decades. But then, in the 1980s, something strange happened. Physicists discovered phases of matter that couldn't be distinguished by any symmetry breaking at all. The first big example was the quantum Hall effect. Here's the setup. You take a very thin sheet of conducting material, essentially a two-dimensional electron gas. You cool it down to extremely low temperatures, and you apply a very strong magnetic field perpendicular to the surface. Then you measure the Hall conductance, which is basically how well the material conducts electricity in the direction perpendicular to both the current and the magnetic field. What Klaus von Klitzing discovered in 1980, working at the High Magnetic Field Laboratory in Grenoble, was that this Hall conductance doesn't vary smoothly as you change the magnetic field. Instead, it comes in exact integer multiples of a fundamental constant and squared over h, where E is the electron charge and h is Planck's constant. Not approximately integer multiples, exactly integer multiples, to a precision of about 1 part in a billion. Von Klitzing won the Nobel Prize for this in 1985, and the integer quantum Hall effect became a new standard for electrical resistance. It was that precise. Now, here's what's wild about this. The samples von Klitzing was using were messy. They had impurities, defects, irregular edges. In any normal situation, all of that messiness would affect the measurements, but the Hall conductance didn't care. It was quantized to those exact integer values, regardless of the sample's imperfections. And that kind of robustness, that insensitivity to local details, should immediately remind you of something. That's a topological property. The integer that the conductance is quantized to isn't determined by the geometry of the sample or the specific arrangement of atoms. It's a topological invariant. The person who made this connection precise was David Thouless, along with collaborators Mahito Komodo, Marcel Denise, and Peter Nightingale, in a landmark 1982 paper. What they showed, and this is beautiful, is that the integer in the quantum Hall effect is a Chern number. Remember characteristic classes, those topological invariants that live on fiber bundles? The Chern classes are among the most important of them, named after Xiang-Shen Chern, who developed them in the 1940s. What Thouless and his colleagues demonstrated is that when you look at the quantum mechanical wave functions of electrons in a periodic potential under a magnetic field, those wave functions define a fiber bundle over the space of crystal momenta, which physicists call the Brillouin zone. And the Hall conductance is exactly the first Chern number of that bundle. Think about what that means. a quantity that experimentalists can measure in a laboratory with wires and magnets and cryostats, turns out to be computed by the same topological formula that mathematicians invented to classify abstract fiber bundles. The integer is robust because integers can't change continuously. You can't smoothly deform a 2 into a 3. That's why the Hall conductance is so precisely quantized. Small perturbations, impurities, slight changes in the magnetic field. None of that can change a topological invariant. It would be like trying to poke a donut until it becomes a sphere. You can't do it without tearing. Thulis shared the 2016 Nobel Prize in Physics with Duncan Haldane and Michael Kosterlitz for theoretical discoveries of topological phase transitions and topological phases of matter. By that point, the field had exploded. The quantum Hall effect was just the beginning. In the 2000s, physicists predicted and then discovered topological insulators, materials that are electrical insulators in their bulk, but conduct electricity on their surfaces, and those surface states are topologically protected. The surface of a topological insulator hosts electrons that move without backscattering, even when they encounter impurities. Because the conducting states are guaranteed by the topology of the bulk band structure, you can't get rid of them without fundamentally changing the topological class of the material. Charles Kane and Eugene Melet at the University of Pennsylvania predicted a two-dimensional version of this in 2005, and shortly after, Liang Fu, Kane, and Melet extended the idea to 3 dimensions. The first 3-dimensional topological insulator was experimentally confirmed in bismuth antimony alloys by a group led by Zahid Hassan at Princeton in 2008. Since then, dozens of topological materials have been identified: topological insulators, topological semimetals, topological superconductors, and the classification of these phases uses exactly the mathematical machinery that algebraic topology spent a century developing. K-theory, which we talked about earlier as Grothendieck and Atiyah's framework for classifying vector bundles, turns out to be precisely the right tool for classifying topological phases of matter in different dimensions and with different symmetries. There's a beautiful periodic table of topological insulators and superconductors organized by dimension and symmetry class, and its structure is governed by Bott periodicity, the same periodicity that Raoul Bott discovered in the homotopy groups of classical groups back in 1959. So here you have this extraordinary chain of connections. Bott proves a theorem about the topology of Lie groups. Atiyah and Hirzebruch build K-theory partly on that foundation. Decades later, condensed matter physicists realize that K-theory classifies the phases of matter in their laboratories. The abstract and the concrete keep finding each other, and this isn't just intellectually satisfying. It has practical implications. Topological materials are being explored for applications in spintronics, where you manipulate electron spin rather than charge to process information. The topologically protected surface states could potentially carry spin currents with very low dissipation, which would mean electronic devices that generate much less heat. There's also the connection to quantum computing we already discussed. Topological superconductors are the systems most likely to host those Majorana zero modes that could serve as the basis for topological qubits. But let me pull back for a moment and think about what topology looks like today as a mathematical discipline, because it's evolved enormously from Poincaré's day. Modern topology is a vast ecosystem. You have people working on geometric topology, studying manifolds and their classification, still pushing on the questions that motivated the field from the beginning. You have algebraic topologists developing increasingly sophisticated computational tools, spectral sequences, model categories, infinity categories, that would be almost unrecognizable to someone from the 1950s. You have people in symplectic topology and contact topology, studying the geometry of phase spaces in classical mechanics, where the work of Mikhail Gromov and Andreas Floer in the 1980s opened up entirely new worlds. Gromov's theory of pseudo-holomorphic curves, introduced in 1985, gave symplectic topology its own set of powerful invariants, and Floer homology, which Floer developed before his tragic death in 1991 at the age of just 34, connected ideas from Morse theory, gauge theory, and symplectic geometry in ways that continue to generate deep results. And then there's the relationship between topology and geometry that Bill Thurston so beautifully illuminated. Remember Thurston's geometrization conjecture, which Perelman proved? That was about three-dimensional manifolds, but the broader vision, that topology and geometry are deeply intertwined, that understanding the shape of a space means understanding both its flexible topological properties and its rigid geometric structures. That vision has become a guiding principle across mathematics. Thurston himself was famous for his geometric intuition, for his ability to see and think about spaces in ways that other mathematicians found almost supernatural. He once wrote that mathematics is not about theorems but about understanding, and his influence on how topologists think about their subject has been as important as any specific result he proved. There's a thread running through all of this that I want to make sure we don't lose sight of, because it connects to something deep about what topology really is. From the very beginning, from Euler's bridges, from Listing coining the word topology, from Riemann's surfaces, the central question has always been, what properties of a space survive when you're allowed to stretch and bend and deform it? What's left when you strip away all the rigid structure, all the specific measurements, all the coordinates? And the answer, over and over, has turned out to be more than you'd expect. The number of holes, the way loops can or can't be contracted, the twists in a bundle, the linking of curves. These soft, flexible, qualitative features carry an enormous amount of information, and that information turns out to be exactly what you need in contexts you'd never have predicted. In physics, where the topology of a fiber bundle tells you what kinds of particles can exist. In data science, where the persistent homology of a point cloud reveals structure that no other method can see. In quantum computing, where the braiding of anyone's encodes information that's protected precisely because it's topological, because it depends not on the exact path, but on the winding, the linking, the qualitative shape of the trajectory through some abstract space. And that's the thing that still amazes me, honestly. That this subject, which started with a man looking at 7 bridges in a Prussian city and asking a question that seemed almost like a puzzle, almost like a game. Can you walk across all of them exactly once? That this simple, playful question contained within it the seed of an entire way of thinking about the world. Euler didn't know he was founding topology. He thought he was doing what he called the geometry of position, and he wasn't even sure it was proper mathematics. But the instinct was right. The instinct that there's a kind of mathematical truth that doesn't care about distances or angles, that lives at a deeper level, a level where the only thing that matters is how things are connected. That instinct turned out to be one of the most productive insights in the history of human thought. So let me spend a little time here, as we wind down, talking about where topology is right now, today, and where it seems to be going, because the field is alive in a way that would have been hard to predict even 30 years ago. It's not a finished subject. It's not a museum piece. It's a living, growing, sprawling enterprise. And some of the most exciting work is happening at the boundaries, the places where topology meets other fields, and something unexpected emerges from the collision. One area that's developed enormously in just the last couple of decades is what people call applied topology, and the flagship example is topological data analysis, or TDA, which we touched on earlier. But let me say a bit more about why it matters, because I think it illustrates something beautiful about how pure mathematics finds its way into the world. The basic idea, remember, is that you have a cloud of data points, maybe in some high-dimensional space, maybe representing gene expression profiles or sensor readings or the shapes of proteins, and you want to understand the shape of that data, not just the statistics, not just the mean and variance, but the actual geometric and topological structure. Are there clusters? Are there loops? Are there voids? Persistent homology gives you a rigorous way to answer those questions. You build a family of simplicial complexes at different scales. You track which topological features persist across many scales, and the ones that persist are the real signal. The ones that appear briefly and vanish are noise. What's remarkable is that this actually works. It's not just a theoretical curiosity. In 2008, Gunnar Carlson and his collaborators used persistent homology to analyze a data set of natural images, small patches of photographs, and they found that the space of high contrast patches has the topology of a Klein bottle. A Klein bottle. This non-orientable surface that you might have thought was just a mathematical curiosity, something you'd see in a topology textbook as an example of a weird space, it showed up in real image data. And that topological structure tells you something meaningful about how natural images are organized, about the relationships between different kinds of edges and gradients in photographs. That's not something you discover with standard statistical methods. You needed the topological lens. Since then, TDA has been applied to everything from neuroscience, mapping the topology of neural activity patterns in the brain, to materials science, where the arrangement of atoms in amorphous materials has topological features that correlate with physical properties like strength and conductivity. There's work in oncology, where the shape of tumor vasculature, analyzed topologically, can help predict outcomes. There's work in cosmology, where persistent homology is used to study the large-scale structure of the universe, the cosmic web of galaxies and voids that stretches across billions of light-years, the topology of the cosmos. Think about that for a second. The same mathematical ideas that Poincaré developed to classify abstract spaces are now being used to understand the actual shape of the universe we live in. And then there's the quantum computing angle, which is still in its early days but is potentially transformative. The idea of topological quantum computing, which we talked about, using anyone's whose braiding encodes quantum information in a way that's inherently protected from errors. This is still largely a theoretical program, but there's been real experimental progress. Microsoft has invested heavily in this approach, betting that topological qubits, once they can be reliably created, will be far more stable than the alternatives. The key challenge is engineering materials that support the right kind of exotic quasi-particles, Majorana zero modes specifically, and there have been promising results in semiconductor-superconductor hybrid structures, though also some setbacks and retracted papers, which is how science goes. The road is bumpy. But the underlying mathematical framework is sound, and if it works, it will be one of the most dramatic examples in history of abstract pure mathematics becoming the foundation of a practical technology. Topology protecting your quantum computations. Euler would be astonished. But I don't want to give the impression that topology's modern significance is only about applications. The pure mathematics is thriving too, and some of the deepest questions remain open. Here's one that gives you a sense of how much we still don't know. Remember the homotopy groups of spheres? We talked about how even something as simple as a sphere, the most symmetric, most perfect geometric object you can imagine, has homotopy groups that are incredibly complicated and essentially unpredictable. We know a lot of them, thanks to decades of work with spectral sequences and other heavy machinery, but we don't have a complete picture. There's no simple formula. The homotopy groups of spheres remain one of the great mysteries of mathematics, and new computational and theoretical tools are still being developed to chip away at them. One of the most exciting recent developments in this area involves something called motivic homotopy theory, which was pioneered by Vladimir Voevodsky in the late 1990s and early 2000s. Voevodsky, a Russian-born mathematician who won the Fields Medal in 2002, found a way to import the tools of homotopy theory into algebraic geometry, a completely different branch of mathematics. The idea, very roughly, is that algebraic varieties, the solution sets of polynomial equations, can be studied using the same kind of topological thinking that Poincaré brought to manifolds. Voevodsky used this framework to prove the Milnor conjecture, a deep result connecting algebraic K-theory to Galois cohomology, and the methods he developed have opened up an entire new landscape at the intersection of topology, algebra, and geometry. It's exactly the kind of unexpected cross-pollination that has characterized topology's history from the beginning. And speaking of unexpected connections, let me mention one more area that's been developing rapidly: the relationship between topology and information, in a broad sense. There's a growing understanding that topological ideas are fundamental to how we think about the structure of information itself. In theoretical computer science, for instance, topological methods have been used to prove impossibility results, to show that certain distributed computing problems literally cannot be solved, not because we haven't been clever enough, but because the topology of the problem space prevents it. This goes back to work by Herlihy and Shavit in the 1990s, who showed that the impossibility of certain consensus protocols could be understood as a topological obstruction related to the same kinds of ideas that Brewer was working with a century earlier. The fixed point theorem, the idea that continuous maps on certain spaces must have fixed points. This turns out to have direct implications for what computers can and cannot agree on. There's something poetic about that, I think. The same Brouwer who gave us intuitionism and had philosophical doubts about the foundations of mathematics also gave us a theorem that, decades later, would illuminate the fundamental limits of computation. Mathematics has a long memory. Ideas planted in one century bloom in another, often in soil that the original gardener never imagined. And that brings me to something I've been wanting to say throughout this whole journey, something that I think is the real takeaway, if there is one. Topology, more than almost any other branch of mathematics, teaches you to see the world in terms of what's essential versus what's accidental. When you look at a coffee mug and a donut, and you say they're the same, topologically the same, you're not being silly. You're making a profound choice about what to pay attention to. You're saying, I don't care about the material, the color, the exact dimensions. I care about the structure, the whole, the connectivity. And that choice, that decision about what matters and what doesn't, is at the heart of all good science, all good engineering, all good thinking, really. Every time an engineer builds a bridge, they're making choices about which forces matter and which can be neglected. Every time a physicist writes down a model, they're deciding which features of reality to include and which to abstract away. Topology takes this to its logical extreme. It asks, what if we abstract away everything except the most fundamental structural features? And the miracle, the genuine recurring miracle of this subject, is that what's left is not trivial. What's left is rich and deep and endlessly surprising, and time after time turns out to be exactly what's needed to solve problems that seem to have nothing to do with stretching or bending or deforming. You know, there's a beautiful passage from Poincaré, the man who arguably did more than anyone to create this field, where he talks about the value of mathematics. He wrote that the scientist does not study nature because it is useful. He studies it because he delights in it, and he delights in it because it is beautiful. And topology, I think, is one of the most beautiful parts of mathematics. Not beautiful in the way a painting is beautiful, or a sunset. Beautiful in the way a deep idea is beautiful. The way it connects things you thought were separate, the way it reveals hidden structure, the way it takes something complicated and shows you the simple truth underneath. From Euler's bridges to Perelman's proof, from Riemann's surfaces to topological insulators, from Poincaré's loops to quantum computing. 300 years of human curiosity, stubbornness, genius, and collaboration, all woven together by this one strange, wonderful idea, that the deepest truths about shape don't depend on measurement. They depend on connection, on holes and handles and twists and links, on the things that survive when everything else changes. And if you've drifted off by now, that's perfectly fine. That's what this was for. But if some small piece of this story stayed with you, the image of Euler walking through Königsberg, or Riemann standing before that skeptical audience in Göttingen, or Emmy Noether insisting that algebra was the key, or Perelman quietly posting his proof and walking away, if any of that lingered, then maybe the next time you pick up a coffee mug, you'll smile, just a little, thinking about donuts and dimensions and the strange, beautiful mathematics of shape. And with that thought, with the quiet knowledge that the world is richer and more connected than it appears, that there are deep structures hiding in plain sight, waiting to be noticed by anyone curious enough to look, you can let your eyes stay closed, let your breathing slow, and let the topology of your dreams carry you wherever it wants to go.